Good evening. My name is Simone Hill, and I am an undergraduate astronomy TA at UNL. I want to welcome you to the 2023 Ruckman Public Lecture. The Jerry E. Ruckman Lecture Series is sponsored by the UNL Department of Physics and Astronomy and made possible by the generous endowment of 1962 UNL BS Physics major Jerry Ruckman. Each fall, we host a nationally recognized educator speaking on public science topics or physics education issues. Our guest this evening is Daniel Reichart, Professor of Physics and Astronomy at the University of North Carolina at Chapel Hill. Dan is a well-known leader in the field of robotic telescopes, directing the Skynet Robotic Telescope Network, an online collection of nearly 20 fully automated optical telescopes, up to 1 meter in size. Tonight, Dr. Reichart will be sharing with us some work he has done on the Stonehenge Observatory, recreating the solar and lunar alignments that were observed by Stonehenge's architects thousands of years ago. Please welcome Daniel Reichart.
Turn this one off. All right. I'll come down here. I'm wearing my reading glasses. I can't see a damn thing unless I get close. I'll get back up there in a second. My first question for you is, what the hell are you doing here tonight? There's a football game. So thanks for coming out despite that. If in half an hour I see some of you sneaking out or checking your phones, I understand. Let's see. Let's get to know the audience a little bit. I know there are a lot of students here. I know there's extra credit. I've never taken so many selfies for a talk before. I know that's not because you want your selfie with me, but it's extra credit. So how many anthropology, archaeology people do we have here? A couple. Okay. Yeah, good for you. How many astro or physics people do we have? Okay, a good number. Who are the rest of you? Who the hell are you? What other majors do we have here?
Chemical engineering.
So we got some chemistry, architect, okay. Computer science, there's a little bit of this and that, a little that and this. Okay, good. Well, thanks for coming. Today we're just going to do kind of a relaxed, fun stroll through the astronomical properties of Stonehenge. Now, a bit of a disclaimer. I'm not an archaeologist. I'm not an anthropologist. Great respect for these people. They did so much important work that I integrated into this. I am an astronomer, professional astronomer, so I supposedly know that. But my astronomical knowledge of archaeological sites is rather limited. It's limited pretty much just to this particular site, to the happenstance of how I started working on this. I started working on this, I don't know if you can tell from the software there, it's quite old. Yeah, some of you saying, yeah, that looks pretty old. I started working on this when I was an undergrad, almost, oh my God, 30 years ago. I was an undergrad at Penn State, and they had this winter program where you could go to Britain for 2 weeks during the winter at very low cost. They would book the flights and the rooms and the tours years in advance to keep it pretty cheap. They didn't tell you the other reason it was cheap is you're staying in rat-infested motels with bugs crawling on the walls. But anyway, I signed up and it was pretty good. Thing is, you had to do a project, like a thesis, like a mini thesis. And I was a triple major. I spent 5 years as an undergrad getting science degrees. And the last thing I wanted to do was another long paper or thesis. So I thought I'd beat the system. I went in, talked to the director and said, instead of writing a thesis, could I write a computer program? I hear Stonehenge is kind of astronomical. There's something there. Could I just write a program to simulate Stonehenge in 3 dimensions? This is not 3-dimensional. This is an overhead view. You plan it and you hit the submit button, and you could put yourself at any place, look in any direction and see it in perspective in 3 dimensions. I said I'd simulate the sun and the moon. We'll just see. They've been saying since the 60s there are astronomical alignments. If you stand at the right place and look at the right time, like first day of summer, first day of winter, the equinoxes, or similar dates for the moon. You stand at the right place, look off in the distance, and you'd see a marker marking it as it comes up over the horizon. This is solar and lunar horizon astronomy. So I figured I could code that in. I could find the archaeological records, code that in, easy peasy. And I'd be done and get out of having to write a thesis. Well, it was a good trip. I got to see Stonehenge and all the other students who went on the trip, a couple months later, they were done with their theses and still working on my computer program. The end of the semester arrived and I had to ask for a semester extension. End of that semester arrived, had to ask for a semester extension. So my first real effort to get out of work was an abysmal failure. It took about 1.5 years to write this. And there's still a few things I'd like to change, but damn it, the programming language that I use doesn't even exist anymore. Visual Basic 5, does anyone even know what that is? Is there a computer scientist in here somewhere? Anyway, you probably don't even know what that is. So I can't even modify it, but it works well enough that we can play with it today. So that's the plan. Let's just dive right in. I'll show you some of the basic functionality. We'll learn some more about the architecture. We'll learn some more about the astronomy as we go along. So as I said, this is an overhead view of Stonehenge based on the best archaeological records of the 90s. Not much has changed since then. The archaeologists they're just amazing. You know, I stand there and I say, this is a piece of ground with grass on it. But they can, with their equipment and their excavations, they can say, actually, there's a hole right here. And they excavate in and find little fragments. And they can say, oh, there's a post in here, or like a wooden post or a metal stone. And they can tell you what kind of metal, even if it's been gone for centuries. Often they find things underneath like antlers or something that was used to scrape open the hole, and they can do radiometric dating and tell you when it was put in. Super impressed with the archaeologists who gave me the information. Again, this is just an overhead view. You're not seeing how high the stones are. And, you know, many of the stones still remain, so you can figure out how high they are because they're there. Though many are gone. Some are there, they've toppled over. But many are gone, but there are a lot of repeated structures. If one's gone, you can just look at the one next to it to figure out how tall it would be. The trickier ones are these outlying stones. These are the astronomical alignments, or I hope to convince you, these are the astronomical alignments where if you stand like here at the center and look in the outskirts, you can see on these special astronomical days, the sun or the moon rising or setting over them. Most of them are gone. And even though we knew where they were, I had to guess how tall they were. But usually it's pretty easy. I just guess they're as tall as the horizon. If you stand at the right place and make it flush with the horizon, the alignments, as you'll see, just tend to work. So a little bit of guesswork, but not too much. The archaeological record's pretty complete for this site. Okay, so the way it works, this is a zoom in. This is, you know, when I say Stonehenge, you think of the big stone circle, right? And that's actually phase 3 of Stonehenge. Stonehenge, okay. So after I wrote this, English Heritage renumbered the phases and whatever. I'm going to use the old nomenclature. Back then there was phase 1, 2, and 3. Phase 1 was built around 3100 BC and eventually out to phase 3 about 2000 BC. The Stonehenge you know is called phase 3, built around 2000 BC. It's the stone circle. Again, this is the overhead view of the inner region. And then zooming out a little bit, you have the astronomical stones. These brown things are holes that were dug in the ground. They actually never put anything in those particular holes. They dug them in this interesting opening spiral pattern that we'll talk more about. But to use it's pretty simple, at least initially. Pick where you want to stand, pick the direction you want to look and simulate. And here you are, Stonehenge, around 2000 BC. Now, in the 90s, there were no graphics engines. So I had to code this all myself. Don't expect to see the grass waving in the wind or shadows or bumps and lumps on the rocks. I had to approximate everything as rectangular solids. But yeah, it's tricky writing your own graphing engine. You have to first get all the corners. You can make a wireframe model. You have to code perspective. The hard thing is teaching it to paint the backs before the fronts of the rock, the tops before the bottoms. Unless you're above it, then you need the bottoms before the tops to paint everything so it looks right. But the younger version of me was apparently smarter and figured it out. Okay. Now, let's take another view here. We'll end this simulation. Let's stand kind of here on the inside and take a look. Okay, so here we're seeing stuff in the inside. You have these smaller stones. These are called blue stones. They were actually brought in phase 2 from far away in Wales. They have a blue, not in my simulation, but in reality, they have a blue tint. And back when I wrote this, they wouldn't let you in on the center. You had to do a lot of paperwork to get in the middle. They've since opened it up. If you go to Stonehenge now, you can probably stand in the middle. But back then, people were scraping the blue stones because people thought they had magical healing properties. So people would scrape it and eat rock. Humans can be so stupid. But there were like inscriptions on some of them, and they were ruining them, so we weren't allowed in the center. So a simulation is actually the only way you back then could have a view like this. But now you can go and see. It's sort of, because a lot of it's fallen down. Not all the stars. So the outer ring, the uprights here are called sarsens. The cross pieces above them are called lintels. And these giant archways, there are 5 of them called trilithons. A lot of the stuff has fallen down over the years. Even if you went there now, it wouldn't look this way. This is how it best, rectangular solid approximation of what it looked like when it was built. Now, sun and the moon. This was an adventure for me. You see the sun is actually moving across the sky. Every 5 seconds, the cursor blinks and the sun moves a little bit. The moon's also somewhere. I think it's actually right about here. If I adjusted the simulation, you could see it, but you'll see it a little bit later. Those were hard to get in there. And I'm an astronomer. It should have been easy. Now, nowadays, you just grab an astronomical computer library and plug it in, you're good to go. They didn't exist back then. You had to actually go to the physical library and check out a book. But first I thought, okay, sun and moon, they go around the sky. So I just coded circles. The sun going on a circle around the sky, moon going on a circle around the sky, and no alignments. And I thought, oh, stupid me, I'm an astronomer. They don't travel on circular orbits. Does anyone know the shape of the orbit? Planets go around the sun, moons go around planets. Not a circle, but what was that? Oval. There's a geometric term, ellipse, which is a kind of oval. And so I put ellipses in there and thought, okay, now I got this. No, didn't work. It's actually more complicated. The ellipses come from Kepler. Kepler figured out their ellipses. Newton figured out why when he invented physics and calculus and like everything else. Newton was amazing. But this is what we call a three-body problem. It's not just the sun tugging on the Earth and the Earth tugging on the moon. The sun tugs on the moon, which has back reaction on the Earth, which has back reaction, et cetera, et cetera, et cetera. Three-body problems are really complicated. There's no, what we say, closed form. That just means there's no easy equation. You can go to the library back then and check out an obscure book that gives you the orbits of the sun. I mean, we orbit the sun, but the apparent motion of the sun in the sky and that of the moon. The sun equation is not too bad. The moon equation is like 100 pages long. And term after term after term, the more terms you include, the more accurate it is. So I spent a lot of time typing in that moon equation. If you get one sign wrong, the moon goes the wrong direction. This is how we had to do it back then. But I got it all in there, the sun and moon correct. And so, okay, where are my alignments? Because the alignments have been known since the 60s. I just had to check them. Well, all but one. There's one alignment that I discovered with this program. I never published it. No one knows it except people who attend my Stonehenge talk whenever I give it every couple years. So you'll be part of an elite group, but I'm saving it for the end. So don't try to sneak out early. Okay, I still didn't have the alignments. I had the correct moon, sun, but no alignments. I'm just telling you the things that go into it before we explore. I was still missing two things. The first thing was the tilt of the Earth. Does anyone know the tilt of the Earth is how many degrees? 23.5, yeah. It's not always 23.5. Sometimes it's as low as 23, as high as 24. The Earth, the equations for the Earth are exactly the same as the equations for a top. Introductory physics students have to figure out the equation of a top. And I know about tops. I'm half Jewish, which means I didn't go to synagogue or anything. It means I gambled for pennies with dreidels on Hanukkah. That's kind of the extent of my religious education, gambling for pennies with dreidels. And dreidels are tops. So I learned a little bit about tops. Maybe that's one of the reasons I became a physicist. So you can spin a top. It spins pretty fast. Imagine a top on an axis, give it a spin, it's spinning. The Earth does the same thing. It spins once a day. It's tipped on an axis, spins once a day. But what do tops do when you spin them? Let's say this is the rotation axis. What does it do? Oh, you used the correct word. Good. It precesses. So it's spinning very fast, precesses more slowly. The Earth does the same thing. It spins once a day, precesses every 26,000 years. It's because it's so close to being spherical. Perfect spheres don't precess. We're not quite perfect. We're a little fat around the middle. It's the same as me. But it precesses. So, the rotation axis points to the North Star. But in 1,000 years, it will point some other place in the sky. And the North Star won't be the North Star. And after 26,000 years, comes back, it's pointed at the North Star again. It says precession. There's one more motion. As it's precessing, what does it do? Ever notice this? It wobbles. I think the technical term is nutation, but it wobbles just a little bit as it precesses. Earth is doing the same thing. It wobbles between 23 and 24 degrees. And back then, when they built this, I think it was closer to 24. You go to Stonehenge today looking for the alignments, none of them work because the Earth has tipped over. No fixing that in reality. But in a simulation, no problem. I just type, and I have the equation for the tilt of the Earth. Okay, so in the simulation, the tilt of the Earth has been corrected now. Now it's like, okay, alignments. Still missing one final thing. The alignments were there. They're just a little bit off in position, a little bit off in time. And the reason why, I was missing an atmosphere. And you don't think about the atmosphere, but the atmosphere refracts light. It bends light. Ever see a straw in a glass of water, how it looks bent as the light transitions from the glass to the air? A lot of atmosphere bends light. If you look up, there's not a lot of atmosphere. The atmosphere is really thin. That's part of the problem with global warming. There's not much there. But if you look across the horizon, and all these alignments are on the horizon, you're looking tangentially across the Earth. And so you're looking through a lot of atmosphere, and it bends the light. Ever watch a sunset? Yeah, you've all watched sunsets. And it sets, you say, oh, that was pretty. Well, you may not realize this, but it actually set like a minute or so earlier. And the light refracted up from below the horizon into your eye. So it coated in a basic atmosphere, and then all the alignments work. And I'm not saying all this just because, look how smart I am. I'm just saying there's a lot that goes into it, much more than I thought when I signed up for it, but it's all there now so we can play with it and see alignments at Stonehenge. Okay, well, a couple things before alignments. Let's learn the different phases. I'm going to end this simulation. Cancel. So there are many places you can stand. You can use the mouse as we have. Stonehenge 1, 2, and 3, they have centers, and those are prime places to stand. The station stones, these 4 stones here, 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 and here, forms a rectangle. Those are also good places to stand. Some are marked with little earthen mounds saying, I'm important, stand here. But for right now, let's do other. I'm going to go 500 feet along the main axis. That's off the top of the screen, and stay on it. I'm going to turn around and look back. Use my mouse that I brought. Try to get nice and precise. I'm a perfectionist, that's the problem. There we go. And you have eye height options. You can stand on the ground, lie on the ground, sit on the ground. You can also climb up on the lintels. They'll never let you climb on the cross pieces at Stonehenge. But in here you can, and that's actually where I found the one alignment no one knows about. But right now, I'm just going to hit other. I'm going to go up 50 feet, simulate. So now we have a bird's eye view of phase 3 of Stonehenge, again, 2000 BC. Here you can really see the Saracen Circle. You can see the great trilithons, or the 5 trilithons, the big one's called the Great Trilithon. People wonder why it's as big as it is. I'll tell you at the end. And here we have some holes in the ground, dug but never used, and the outlying stones, which are good for the alignments, as you'll see. Let's work our way back in time, because this is actually not the most astronomical phase. Let's go back to phase 2. So there's the moon and its phase. Phase 2 was a few hundred years earlier. It's before they dragged the Sarsens. The Sarsens, the big, those are 50 tons apiece. They dragged them from about 25 miles away. Back here, what they've introduced, this is where they introduced the outlying stones, the astronomical stones, and most of these blue stones. They're in a different configuration, a semicircle. And they brought those, they're about 7 tons apiece. They brought those all the way from Wales. Come back to phase 2 in a second. Let's go to phase 1. Now we're at 3,100 BC or so. And this is how it began. Well, sort of. There's actually activity at the site going back thousands of years to Mesolithic times, 7,000 something BC. When they excavated the parking lot, because they can't just lay down a parking lot, they have to carefully study the ground before they do so, they found some holes. And one was a tree hole, but the others were man-made in a due east-west line. So even going back thousands of years before this, people are at the site doing stuff. They understood the cardinal points of the compass even back then. Anyway, this is phase 1, 3,100 BC. There's not much here. You have 2 stones here. So if you stand at the center, these 2 stones here frame due northeast. Nothing astronomical. In fact, those might be the only 2 stones at all of Stonehenge that have no astronomy associated with them. Then you have these 2 stones here on the main axis. They frame summer solstice sunrise. First day of summer, sun coming up, stand in the middle, comes up right between these 2. And I'll show that. Then you have these posts, and these are tied to a lunar alignment. Lunar alignments are really rare. You don't see them a lot in archaeoastronomy around the world. Solar alignments, you see all the time. They had a good reason. Not Stonehenge. Stonehenge, they went nuts. The whole thing, 1.75 million person hours of labor to build all that. But in the British Isles alone, there are hundreds of very simple 2-stone archaeoastronomical sites. You stand at one stone, look at the other one off in the distance, marks the first day of summer. Stand at that one, look back, marks the first day of winter. Summer solstice sunrise, winter solstice sunset. Why would they build these all over the place? Why would you need to know when summer started, when winter started? Why would you need to keep track of the calendar that accurately? Farming, these are agrarian societies in tough conditions. And this is pretty far north, gets cold. If you plant your crops a couple weeks too early or too late, more people than usual die come winter. So you needed a basic calendar. Here they mark it with stones. Other places, they just remember, oh, when the sun comes up over that nook in the mountain range, first day of summer. When it comes over near that whatever, first day of winter, first day of spring, fall, etc. They just remember. At least we think they did. You know, there are no written records, except with the Hopi Indians. They kept this practice up long enough. We do have written records of them using portions of the landscape to keep track of the seasons. So this is a very common thing. Now, at Stonehenge, they went above and beyond. So I'm not here saying Stonehenge was primarily astronomical. Archaeologists and anthropologists, at least historically, hated that. So the 2 or 3 of you, don't worry, that's not what I'm saying. They went above and beyond. This had to be some kind of religious site or political, maybe near the end, economic. It stood at the crossroads of trade with Europe back then, between Europe and Ireland. It could have been all sorts of things. I'm just saying that when they built it, they had astronomy in mind. So phase 1. Oh, you also got 56 holes in the ground. Those are called Aubrey holes, named after the 18th century antiquarian who found them. And there's one more structure. Oh, I should say the horizon back there is the actual Stonehenge horizon. That's it. You got to have the real one to get all the alignments to work. But there's one structure I could not simulate because I could only do rectangular solids with the programming capabilities back then. So I drew it. I'll open up the manual. Let's see, main menu, history. We'll use this manual a couple times today. Oh, here's a map of the car park. Brits call it a car park. We call it a parking lot. You can see the holes, the tree hole and the holes they discovered in the 60s that were dug, 7,000 BC. But anyway, this is the part I couldn't simulate. So I hired the best artist I could afford as an undergrad, who is myself. And this is called a henge. It can be confusing. Stonehenge, hanging stones. You go to Stonehenge, stones hanging over top of you. Think hanging means henge. But henge can also mean the earthen barrier around it. And these were common structures. They built them all over the place to keep livestock. This one has an opening due south and one for summer solstice sunrise. Not quite northeast, but where this, if stand at the center and the sun comes up to that one. I've drawn like a little person for scale. The inner mound was 6 feet tall. Back then, people were shorter. You couldn't see over it. You can only see through those two openings. The outer mound's about 3 feet tall. And it's hard chalk. The ground is hard chalk. So when they first built this, it'd be gleaming white. But very quickly, it would cover with dirt and grass and wear down. By Stonehenge 2, it was worn down that you could see out. But originally, you couldn't, just along that particular opening. Here's what it looks like today. Just a narrow ditch in the ground. You see a burial mound off in the outskirts. There are a lot of these there as well. That's the one part you don't see. I'll hide the manual. Okay, ready to see some astronomical alignments? No, you don't know any astronomy yet. So I got to teach you some astronomy first. Got you all worked up for nothing. Okay, Stonehenge astronomy. In particular, sun and moon astronomy on the horizon. Let's see, I got a laser pointer here. This will help. I don't know the orientation of this room, but we're going to pretend that's east and west is behind you. Sun rises in the east, sets in the west. That's true how many days out of the year? Only 2 days. On the equinoxes, the first day of spring, first day of fall, rises due east. We're in the northern hemisphere, so we see the sun over the southern sky, travels like that, sets due west. I'll try not to blind anyone with this green laser pointer. Okay, that's how it works. Now, in summer, let's say I'm the Earth. Earth is tipped. It's tipped towards the sun. And so from our point of view, the sun will be higher in the sky. It rises north of east, travels much higher, longer path in the sky, sets north of west. You just have a little bit of time where it's underground. And we all know the days are longer in summer and the sun gets higher in the sky. Okay. Winter. In winter, the northern hemisphere is tipped away from the sun. So the sun is lower in our sky. I'll tip back over. And so it rises south of east, does a little path across the southern sky and sets south of west. It's only in the sky a little bit, doesn't get very high. That matches your experience, right? Okay. So all the markers are on the horizon. They're not marking anything up, just on the horizon. The rise point and the set point change throughout the year by a lot. Up there, 50-some degrees latitude, it's 80 degrees on the horizon. So if they can remember or mark where the sun is at different points, then they have a calendar. You can do this yourself. You can make your own archaeoastronomical site, pick an observing point, mark it with the stone. Let's say summer's approaching. This is how they must have done it. Summer's approaching, so the sun's rising more and more north. Before dawn, got to get up before dawn, get your friend up, send them downfield. The farther, the better. We'll talk about why in a second. And as the sun's coming up, you say a little bit to the left, a little bit to the right. Okay, right there, mark it. You mark where you're standing, you mark where it came up. Come back the next day, as you're getting closer summer, they have to move their marker to the left, to the north, more and more and more, until eventually it stops at this position before it heads back. And it will stay there for a few days. It stands still. What's the old word for standstill? Any guesses? Solstice, right? We call it the summer. You've heard summer solstice, winter solstice. Solstice means standstill. It's standing still on the horizon. Actually, here's a fun story. Winter. So as winter's approaching, it's rising farther and farther to the south. And the days are getting shorter and darker and colder. Food reserves are dwindling. People are dying. It's bad. The sun rising going in this direction is bad. And so eventually it gets to the southernmost standstill point, solstice, stays there for a few days. The human eye can't distinguish it for a few days. What's the day of the winter solstice? December 21st. So you can't see any motion until about the 24th. And you see it, and then the next day you have a big party. So they had a big party on December 25th, celebrating the fact the moon's going back this way, better days are coming. It's going to get warmer, people stop dying, it'd be great. December 25th, that's a holiday for us, right? So, birth of Jesus. When was Jesus born, according to biblical scholars? Not then. I forget when it is. I think it's April or something like that. But the early Catholic Church saw this great big holiday. They wanted to supplant it and people follow their religion. So they said Jesus born on the 25th, and they succeeded. We no longer celebrate this pagan holiday of longer days are coming. Instead, we celebrate Christmas. So, that's origin of Christmas holiday, or at least when it was chosen. All right, so let's see how this works here. I'll move from summer, fall, winter, standstill, spring, summer. Pretty easy. Okay. More complicated is the moon. The moon goes over a similar path, not once a year, but once a month. Now, to us, the month is how many days? It depends on what? Okay, not the calendar month, the lunar month, the phase cycle from new moon to new moon or full moon to full moon. It's how many days? 29 and a half. Notice that's not 29 and a half. So this is the time the moon takes to go around the Earth with respect to the background stars. During that time, Earth is on its way around the sun, so the moon has to go a little bit farther to get back to the same phase. So in terms of its position on the horizon, it's 27 and a third, not the phase cycle of 29 and a half. But anyway, over that 27 and a third period, it does the same thing. It has a northern point and a southern point. Now, what makes the moon more complicated, and this is kind of the last, well, it's not the last. I'm going to show you a few more things, and then you get the alignments. What makes the moon more complicated? You have the sun-Earth plane, you have the Earth-Moon plane, and they're tipped 5.5 degrees. And this plane, as it's going around, as the Earth-Moon system's going around the sun, it precesses as it goes. It's also a top. And we don't have to go through all the details, but the result of that is the endpoints change. It's not always 80 degrees on the horizon. To precess completely around, we call that a Saros cycle, and it's 18 2/3 years, at least in terms of horizon astronomy. So sometimes the moon is going a full 100 degrees on the horizon over its 27 1/3 month. If we go 9 1/3 years later, it's only doing 60 degrees on the horizon up at this latitude. And they learned this the hard way. For whatever reason, they started marking the lunar alignments. This is rare. Solar, I think I started this line of thought, but I didn't finish it. Solar alignments are common for calendrical purposes. The moon has it's no use as a calendar. You can't break the year into an integer number of months. You get 12 and a bit. And so very few sites studied the moon, but I'm going to convince you the moon is built into the Stonehenge architecture. It means they got interested in this for non-practical reasons. They just got interested in it because it's there, and they started measuring it. And you can see in the archaeological record, it's fascinating looking at all the holes. There are a ton of holes in this one part of Stonehenge where they marked the northernmost reach of the moon. And then they came back the next year and checked it, and they're like, oh, it's here. And next year they checked it, oh, it's here. You can see them moving their northernmost marker, putting new holes in the ground over this generational period, 18 2/3 years. They learned, they didn't know what caused it. We now know it's because of complicated orbital motions. They didn't know what caused it, but they learned that the endpoints oscillate. If we don't worry about the monthly span, I'll just show you here how the endpoints oscillate over 18 2/3 years, both on the northern side and the southern side. It's fun. You can see in the archaeological record, people 3,000, 5,000 years ago learning this. So then all you have to do are these alignments. You put some kind of marker. Here are the alignments for the sun. We got summer solstice, spring or fall equinox, winter solstice. etc. With the moon, they would mark not the northernmost, but the maximum northernmost, maximum southernmost. Only happens once every 18 2/3 years. Or that also mark the minimum. Nope, not this one. The minimum. Here we go. Northernmost, minimum, southernmost. So those are all the places you can have markers. That's the complete sun and moon set. Only last bit is what kind of marker did they use? Well, you have lots of options. Here's your basic marker, just a stone. You can also have framing markers, put a stone on either side. You have secondary, you have an initial marker, but then as the sun rises, it kind of rides along and hits these other stones taller as they go. And lastly, there's only one of these at Stonehenge. You have a boxing alignment. Half disc boxing alignment. You can have stones, you can have posts, you can have a zero, and the last thing is you can have zero disc alignments, just the first glimmer above the marker. You can have half disc, you can have full disc. So that's the full range, and I'm going to show you versions of all of these there at Stonehenge. Okay, you ready for alignments now? Yes, do you understand? You got all that astronomy? I dumped a lot of astronomy on you quickly, hopefully it all absorbed. So now, as your reward, you get to see the markers, or you get to see the alignments. So let's start with Stonehenge 1. Only 2 alignments here. We're going to stand at the center of Stonehenge 1. The event, oh, I jumped ahead. So this is 3100 BC. There's no year 0, and I was too lazy to code it to skip. So when it says negative 3099, that's minus 3100 BC, January 1st at noon. Standing here, we want to look at the summer solstice alignment. So I just need, when did the summer solstice occur? In 3100 BC, month, hour, minute, day, second. I need it to the second. Anyone got that? No. What do they teach you here? No, I'm kidding. It's all here. Event, sun, summer solstice, sunrise, next. Okay, it set the time for us. Back then it was June 24th, not 21st, due to calendar reasons. And also notice it's 3:30 in the morning. No time zones in this calculation. And time zones are like half a daylight savings time. All the time zones are pushed in one direction. No daylight savings time. We're pretty far north. The sun actually did rise at 3:36 a.m. if you take out the time zones and the daylight saving time. Okay, now let's put our eyes back on the ground, and we're going to look at the sun. And this is where it all began. Well, okay, we're zoomed out a little far. So let's change our field of view. Let's zoom in, maybe a 15-degree field of view. Oh, there's the sun. Here it comes. Nice thing with the simulation, I can make time speed up. I wish this was continuous, but back then the computers were so slow, you didn't dare update more than every 5 seconds. So this will bounce along. Give it another instant, and there it is. Half disc framing alignment, frame between this stone and this stone, half disc alignment, Stonehenge 1. Again, these stones here are not astronomical. Northeast is here. It's like they measured this and said, boy, that's close to northeast. And they frame northeast for whatever reason. That's one of the alignments. The second alignment has to do with these posts. It's a lunar alignment, which again, I said, extremely rare. You don't see these around the world. End simulation, cancel. We're going to stand at the Stonehenge 1 center. The event is moon, maximum, northernmost moonrise. Next, to pick the time. Again, only once every 18 2/3 years. Now let's just automatically speed up time, narrow our field of view so we don't have to do this every time. We're going to look at the moon. Boom, right over that post. Simulate. I always thought it would suck to wait 18 2/3 years and it's a new moon and you don't see anything. So I cheated a little bit, coded in a lunar limb. But what we had here was a 0 disc alignment. There's the limb. And so this one, these are posts. Again, the archaeologists can tell there's wood in the ground here. So probably they just brought these out every 18 and 2/3 years for this alignment. And since there's a bunch of them, this is probably a secondary alignment. They get quite tall. Maybe they couldn't cut the stones that tall back then. And so they used posts and just brought them out when they needed to. The height of this was easy to guess. I just made it flush with the horizon. The others, artistic license. I don't know if, I think I made it such that the moon would ride on top. I don't know if it's half disk or first glimmer. I had to guess a little bit for the heights of those other posts. So just pointing out where it may not be a perfect simulation. And it'll just continue on its way. So those are the two simulations of Stonehenge 1. All good so far? Okay. We'll come back to these Aubrey holes later. Let's go to Stonehenge 2. This is hundreds of years later. And they've brought in all sorts of these outlier stones. These are the astronomical stones, as I'll prove. Every single one has an alignment. Some have two. You could do a statistical test. What are the odds that this collection of stones, given only a handful of viewing points, they all hit alignments from the solar and lunar set, some multiple? You could do a formal statistical test. The odds that this happened by random are zero, essentially zero. And so this proves the astronomical hypothesis in the outskirts. And I'll show you a handful of these. But first, let's talk about these blue stones. They brought in from Wales, and here's a zoom in, and they put in this semicircle. First, let me show you where they came from. Yeah, I said Wales, but let's bring up a map. Event, no. Show manual, main menu, history, 2. Good, you can see the manual. And here's where they came from. And the geologists can check the rocks, and they think they came from this quarry in Prestley Mountains in Wales, hundreds of miles away. And so these are smaller. They're 7 tons apiece. They probably cut them, carved them, trimmed them there, made them as light as possible, put them on barges. There's a river. They floated them down out in the ocean. There's a river that comes here, and you can get within 25 miles of Stonehenge. But then you got to carry them over mountains like this, which would have been miserable. So a lot of people think they probably went the long way around, a couple hundred extra miles, but there's a different river, gets you within 7 miles. It's a straight shot. Now, how do you move them over those 7 miles? People used to think log rollers, but if you put them on log rollers, they just push the logs in the ground, particularly the ones that came in the next phase, which are 50 tons, Sarsens. So we now think they just dragged them. During spring, fall, summer, they're busy. They're working the land. Winter is when you had the excess free workforce. And so the political, religious leaders, whoever convinced them to, for these, go to Wales, get them, float them back, and then just pull them. Now, an Astronomy 101 professor, I wish I had the balls to do this, Astronomy 101 professor about 10 years ago in Britain got a 50-ton block of concrete. And he said, come on up, everyone, got all of his students. He was teaching like 300 students. And by his calculations, it would take a few hundred big burly guys to do this. And back then, they're all working the land, they're big and burly. Nowadays, they sit in front of their computers, they look like me. But he got them, he lashed them to this 50-ton block and mush, and they could pull it. So you can slide these things over the snow and ice. You don't have to make up stories about aliens and things like that. People loved aliens in Stonehenge, but you don't need it. There are myths and legends. There's a myth that Merlin brought them from Ireland magically. And I love how there's always a little bit of truth with the myth. Wales is about as close to Ireland as you're going to get without crossing the water. Merlin didn't bring them. A bunch of poor saps who were convinced by more powerful people convinced them to do it. But some truth to the myths there. And then they put him in this semicircular structure. People always say, I wonder why they never finished it. Maybe it's true. Maybe they didn't finish it. I have a kind of, it's just an idea. Yeah, I can't prove anything. I think this was intentional. To see the alignments, and you can see there's more stones here, there's more to look at. You got to stand there, and only a few people can stand there. You have to be really close to the right spot, or else it doesn't work. We didn't do the finger exercise yet, right? Okay, grab a finger, preferably your own, and put it close to your face, close one eye. Let's say your finger's the marker, and whatever's behind your finger, keep track of. That's where the sun is, let's say. Switch the other eye. Oh, what a big change. So this is like having a marker, but it's too close, and you bobble your head. It makes a terrible alignment. Now move your finger as far away as you can and flip. It still moves, but not as much. You can check between the two. Now cut your hand off and move it really, really far away. And as you flip between observing here and observing here, it stays pretty precise. So these outlying stones, they're so far away, so they are precise markers. Anyway, even with that, you have to stand within a few feet for the alignment to work. And thousands of people hauled these stones, and you can't fit them all there. So in my mind, probably the powerful people, religious leaders, political leaders, economic leaders, no one knows, no written records, but the people organized that got to stand there. There's nothing powerful people like more than watching other people, having other people watch them do powerful, important things, right? I think this may have been left open on purpose. So for all the people who did all the work bringing it, they would stand here and watch the important people do the important things. Again, anthropologists don't yell at me. I'm just speculating here. No written record. But maybe it was intentional. Anyway, let's start looking at alignments. There are a bunch here. I'm just going to show you or represent a few, but I'll mention all of them. So let's start with the basic one. We're going to stand at Stonehenge 2 center, summer, solstice, sunrise next to pick the time. We're going to look at the sun. And before it was a framing alignment, that stone and one on the left. The one on the left is gone. The one on the right is actually still there. Most of these other stones are gone. The only thing that's really left to look at is the heel stone. Here's a picture of it. And this stone, heel for Helios, this is what got everyone thinking about the astronomical hypothesis, but for all the wrong reasons. First of all, it's the only stone left to look at, so your eye's naturally drawn to it. Second of all, the Earth has tipped over since then. The alignment actually occurs over this stone, just by chance. But it's too tall. So someone at some point in history tipped it over such that if you're standing at the center and look at it, it's flush with the horizon, or it fell over on its own naturally. But a triple coincidence. You can go to Stonehenge today and see the summer solstice alignment over the heel stone, but that was never the intent. But it got people thinking about this. Anyway, let's hide this. Let's hide the photo spots. They added 2 more stones here. This is a first glimmer. This is a half disc, and they framed it a lot in the foreground. We'll simulate that. First glimmer of light. You can see it's framed in the foreground by the blue stones. We'll give it one more tick and get a half disc here. And the heel stone's just still hanging out. Okay, that's the primary alignment. What else? This in Stonehenge 1 was maximum northernmost moonrise, so this would be minimum northernmost moonrise. Let's confirm. Remember on the astronomy page, the 3 were close together, minimum, maximum moonrise with summer solstice in between. So event, moon, minimum northernmost moonrise next. We're going to stand at the Stonehenge 2 center, look at the moon. Bingo. There it is. First glimmer. End. Okay. So all these stones have been explained now. Now, what's going on over here? If you think about it, it's a little mini version of what we just did. This stone is these 4 stones are called the station stones. That's the northern, that's the southern. And they have little henges, little barrier, little mounds built around them, indicating their importance, like stand here. If you stand here and look in this direction, it's the same as standing here and look in this direction. Summer solstice sunrise occurs over that stone. Maximum northernmost moonrise, minimum northernmost moonrise. It's a little mini version of this. You can also stand here and look in the opposite direction. Opposite summer solstice sunrise is always winter solstice sunset. Same deal over here. Summer solstice sunrise, winter solstice sunset. So I just told you a bunch more. Let's just look at the one. If we looked at all of them, this would go on forever. You'll just have to trust me on those, but it does make sense given how they're laid out. So the event is a winter solstice sunset next. We're going to stand at the northern station stone, and we're going to look towards the sun, and we're going to simulate. And it's a little bit closer, so the stone's a little bit bigger. And these out here are not perfect rectangulars. It was kind of bumpy and lumpy, but you'll get the idea. It would be a zero disk alignment right there, pretty close to there. Okay. What else can we do from the northern station stone? There's one equinox alignment at Stonehenge. Sun, spring and fall equinox, sunrise next. Stand at the northern station stone. Look at the sun. This is our first example of a stone serving two purposes. This was summer solstice sunrise, half disk from here. But they could have put those stones anywhere on this line, not too close because they don't make for good alignments, but they could put them anywhere out here. They stuck it there so they can also get the equinox alignment. Let's simulate that. Now it looks off at the moment, but as it rises, it's going to move over in this direction, giving us, I think, a full disk alignment somewhere over the stone. Again, here from the center, this is the half disk alignment, the first glimmer, and there's the heel stone from the previous phase. Now, the height is not flush with the horizon because the height was chosen to work for the summer solstice alignment, but it will still do a fairly decent job on the secondary equinox alignment. You see it there. So they can also calendar, they can break it up even farther. The equinox alignments happen halfway between the solstices. They're equidistant, and hence the word equinox. One more. There's one more from the northern stone. I got my notes here. Winter solstice sunrise. So event, sun, winter solstice sunrise, sunrise next. Going to stand at the northern stone. There are only a few more for phase 2, so bear with. Nope, I didn't want that. I wanted the northern station stone. Going to look at the sun. Yep. And so this is maximum northernmost moonrise from this station stone. It's winter solstice sunset from this station stone. There you see, first glimmer. I should also point out, all of these are laid out on a grid. They had a yardstick, a little bit longer than ours, called a Stonehenge rod. It's about the size of a meter. And you see how these are evenly spaced? It's all integer or half integer numbers of Stonehenge rods from the center. And from the center out to this circle here, integer number of Stonehenge rods. You see equal angles here to here to here. This angle here is this angle here. They have everything on a really precise radial grid. Not so precise they couldn't do it. They could lay it out with the technology of the day, but they're really into the geometry and the numbers of it. But anyway, that's another stone that does a double duty. I'll show you one more. I always get this one wrong, so I'm looking it up here. Event is maximum northernmost moon set. Next, we're going to stand. Let's stand at the southern station stone and look at the moon. It starts off here to the left, but as it sets, you'll get like a last glimmer over that stone. So, well, wait till we get back to the planning screen. Well, wait a second so you can see this. Again, its height is set to make winter solstice sunset from the northern station stone work, but this is a secondary alignment there. And what's special These are solar alignments. These are lunar alignments. They form a perfect rectangle. There's only one latitude, well, two, one in the north, one in the south, where these alignments form a perfect rectangle. Stonehenge is built at that latitude. It raises kind of a mystery. I don't have an answer for it. Each phase 1, phase 2, phase 3, were built by a completely different culture. The site was chosen by somebody else. Did they choose it for this special property? They didn't make use of it in phase 1, but it just does happen to work. And they used it in phase 2. So it's a bit of a mystery. But I think we've now hit all of the outlying stones. Are you fairly convinced they're astronomical in purpose? Yeah. If you aren't, the statisticians have checked it out correctly, and it is. Okay. So in other words, if you're not convinced, you're wrong. Let's go to phase 3. Phase 3 is a little different. They added a whole bunch of stuff in the middle, but as I talked about, if your stones are too close to you, they don't make for good alignments. But there's other astronomy in this architecture. In the outskirts, they added these two stones. One's now gone, one's tipped over, and it's called the slaughter stone. It's not what it was used for, but that's what it's called. So let's just get this one out of the way. Now we're now at 2000 BC. Summer solstice, sunrise, next. Stand at Stonehenge 3 center, which shifted spots a little bit in the sun. Simulate. This thing is framed like crazy. Here's the slaughter stone in its comparison. There's the first glimmer and half disc. Can't even see the heel stone anymore. Here are the Saracens. Here are the blue stones. It is just uber framed. So this is still a very important alignment. And in the years after phase 3, for another 500 years, the site was still in use. They built an avenue going out to the river from this point along the summer solstice direction. Okay, that's the only new alignment other than my secret one that I've been saving. Let's see, we're getting near the end, right? Okay. I'll go probably 3 minutes over, but what else is going on? Let's go to the manual. Stonehenge astronomy, phase 3. Although the stones are too close together, they're what we call symbolic alignments. The 5 trilithons, if you happen to stand at the base of each, all the major alignments go between gaps in the Saracens. You can run a statistical test on this. It's iffy. It's 50-50. Maybe this was intended, or maybe we're just guessing after the fact. You don't know. But for one of them, the line of sight doesn't work because they're bumpy and lumpy. But someone at some point in history took a mallet at eye level and cleared the sight lines so it would work. So that's kind of a hint that maybe this was the case. So you have these symbolic alignments. Maybe they did little ceremonies at each one for each of these special dates: solar, solar, lunar, lunar, solar, and solar. Maybe, in which case all those stones are significant. But here's the other thing: numbers. I shouldn't put it up yet. I was going to ask you. There are 2 numbers that for every repeated structure in Stonehenge are built around these numbers. One is 29.5, which you already told me is the number of days in the phase cycle of the moon, the easiest thing to see. And the other is this 18 2/3, which they spent a generation figuring out and built into their architecture. So let's start counting things. They rearranged the blue stones. This is called the bluestone horseshoe. They're 19. That's pretty close to 18 2/3. The circle of blue stones, they're 59. That's twice 29.5. There are 30 lintels. Those are the cross pieces. That's pretty close to 29.5. If you hide the lintels, there are, of course, 30 Saracens. And although I don't depict it here, the southern one is literally half size. They may have meant 29.5 exactly. They dug these holes on their grid. It goes from 14 Stonehenge rods spiraling out to 15, 17 spiraling out to 18. They never put anything in them. Who knows what the plan was? But there are 59 of them. That's twice 29.5. And if you go back to phase one, the only other repeated structure, the Aubrey holes, there are 56 of those. That's 3 times 18 2/3. So you all decide for yourself. The outlying stones, you should be convinced by the statistics, but even the numerology and the symbolic alignments are highly suggestive. So since I'm out of time, I'll just end with the alignment that I found. It's in phase 3. And one day, there's some archaeological evidence on the southern side. There may have been a stairwell at one point. So I climbed up on the lintel, something they'll never let you do at Stonehenge. One day I got tired and sat down. So here I am sitting on the lintels, sat on the main axis, looking back. I said, well, that's winter solstice sunset. Sun, winter, solstice, sunset, next. And let's start with the fisheye lens. I'll give you 2 views. I'll give you a fisheye lens just so you know what it feels like to sit on the lintels, because you'll never do it. And this is what you would take in back when it was all still there. The Great Trilithon's gone. You can see the sun peeking in there. There's the moon. Let's watch one last thing. I'll zoom in so you can see what's going on in that Trilithon. Zoom in, put a 20 in here. And you will get a last glimmer alignment right in this box. People always wondered why the Great Trilithon is as tall as it is. If you're sitting on the lintel, you get almost a perfect box. I had to guess the eye height of the architect. If I guessed a few inches taller, that would have been a perfect box. And it's amazing the strange numbers you could pull out of history. If I really wanted to have fiddled with it, I didn't sit exactly on the main axis. If I sat carefully, the last glimmer would be in the middle. But if I really wanted to, I could pull out the eye height of the architect of Stonehenge 3. Isn't it nifty the numbers you can pull out of history by just making this work for his particular eye height or hers? Anyway, I've come to the end. Thanks for staying the extra couple minutes.